Hello everyone. Today we are going to discuss another GATE 2024 question where you can see this is a circuit where there is a capacitor, there is a resistor and there is a zener diode. But it has been said that the initial voltage across the capacitor is 10 volt and the switch is opened. So when the switch is opened, no current can flow through this open circuit. So capacitor is containing the 10 volt. So when the switch is opened, the capacitor cannot discharge. Okay, so now when the switch is closed, which is given that the switch is then closed at t equal to 0, then there is a possibility a finite discharging current can exist. But first we need to investigate that whether the Zener diode is on or not, means whether any current is flowing through the Zener diode or not. If the Zener diode is reverse biased or is in cutoff and there is no current flowing, then the capacitor cannot discharge anything. Then the total energy which is dissipated in the Zener diode will be zero. But first we need to understand that if the Zener diode is in breakdown or is in forward biased, I'm just assuming, I don't know. First we need to investigate. Then we can say that whether how much current is flowing, and then we can find out the total energy which is dissipated in this Zener diode. Let us assume that the switch is closed and there is a finite current which is flowing from the capacitor. Then you will see that this node is positive and this node is negative. So the N part is connected with the positive voltage and the P part is connected with the negative voltage. So we can say that the Zener diode is in reverse bias. And current can only flow through this diode if this diode is in reverse breakdown. Now let us look at the ideal Zener characteristics, because in the question it is given that this is an ideal Zener diode. So here is the ideal Zener diode characteristics, where you can see that V is the voltage across the reverse biased Zener diode. Okay, so as the voltage across the Zener diode is increasing, and once is increasing but it is less than Vz, then no current can flow through this diode. So in the earlier circuit what we have seen, so the capacitor cannot then discharge because the Zener is off and no current is flowing. As soon as the voltage across this Zener diode, then current can flow and then capacitor will discharge through the resistor and the current will also flow through the Zener diode. And as per the characteristics is given, so if the voltage across the Zener diode is equal to Vz, then any value of current can flow through the Zener diode. There is no restriction. Back to our original circuit, where you can see that there is a source of 10 voltage, say at t equal to 0 plus, there is a source of 0 to 10 volt, and you can see that this Zener diode needs 5 volt for the breakdown. So it is possible for this Zener diode to get breakdown, and the current which will flow through this 10k resistor will be at t equal to 0 plus, that will be 10 minus 5, that is a 5 volt divided by the 10k. So that amount of current is going to flow through that resistor at t equal to 0 plus. This is the maximum amount of current which can flow through this 10k resistor, and after that the capacitor is going to slowly it will discharge. But the Zener diode needs at least 5 volt to remain a current. It might be any current, but if the Zener diode voltage is 5 volt, then only a current can flow. So maximum the capacitor can discharge up to 5 volt. So we can conclude that the initial capacitor voltage is 10 volt and the final steady state capacitor voltage is 5. Now if we replace the Zener diode with a 5 volt battery, say, so and the capacitor is discharging where the voltage across the capacitor is VCT, then maximum the capacitor can discharge when this VCT is equal to 5 voltage, which I have defined here as VC infinite. When it is VC infinite, then there cannot be any current, no current can flow, and this is our steady state value. Since in the question it is given that the Zener diode is ideal, so we should not consider the resistance. Anyhow the resistance is 0 in the Zener diode, so we should consider only the 10k ohm resistor and the 10 microfarad capacitor. So the tau is equal to RC, where the R is 10k and the C is 10 microfarad. Now if we multiply it, it will become 0.1. Let's write down the capacitor voltage equation in a transient analysis, where the initial voltage is given and the final value is also given, and there is a time constant also in the equation. So here tau is equal to RC, and RC comes out to be 0.1, and we know that 1 by 0.1 is nothing but 10. So if we arrange this equation, it will be 5 into 1 plus exponential of minus 10t. It appears that there is a capacitor whose voltage is VCT, and there is a resistor, and there is a 5 voltage battery, okay, which is the Zener diode, because the Zener diode is in breakdown. So now it will be a 5 voltage battery. So there will be a current, discharging current, which will be flowing from this capacitor 10 microfarad, and we know that the discharging current is equal to C in dVCT by dt. And now if you do the derivative, then you will get this particular current, which is IT equal to 0.5 into 10 to the power minus 3 exponential of minus 10t. So the instantaneous power which is dissipated across the Zener diode is nothing but the 5 voltage and the current which is flowing through the Zener diode. So it is the product of both. And the current which is flowing through the capacitor, means the discharging current, that current is equal to the current which is flowing through the Zener diode. Okay, so the energy dissipated across the Zener diode is nothing but an integration of the instantaneous power dissipation across the Zener diode. Calculating the energy dissipated, we would get 2.5 into exponential minus 10 tau into 10 to the power minus 3. And on calculation, we will get 0.25 millijoule of energy. This question was very tricky because there might be a situation where current is either flowing in the entire circuit once the switch is closed, or the current might not flow. Because if the current is flowing, then we know that there will be some energy which will be dissipated in the Zener diode. Okay, so how we can find out? It is just say the voltage is into the current which is flowing through here. So that will be our power, instantaneous power. And if we integrate this instantaneous power, it is because the switch was closed at time t equal to 0, and the total energy, since it is said that the total energy, so we are integrating till infinite. So over there, if we integrate it, then we will get the energy dissipated. But the question is that, say suppose in the question it was given that the initial voltage somehow it is say 4 volt, but it needs at least 5 volt to the breakdown region. So there cannot be, means say here there is a 4 volt, and here it needs at least, say this Zener need at least say around 5 volt. So then here cannot be any current. Then the power dissipated across this Zener is 0, because the current is 0, because no current can flow. Okay, so these are the things we need to check when we will start answering. Then first, these are the first thing that we need to check, we need to cross check, and then we can solve it.